Galaxies contain billions of stars. Stars are held together by gravity. Between the galaxies is mostly empty space. On the largest scales, the universe is expanding. This expansion was first observed by Edwin Hubble in the early 20th century. Galaxies slowly move away from one another over time. The Milky Way is a spiral galaxy. It contains hundreds of billions of stars. Our Sun is located in one of its spiral arms. The galaxy rotates slowly. A full rotation takes hundreds of millions of years. Stars orbit the center due to gravity. This motion is stable and predictable. Stars form inside large clouds of gas and dust called nebulae. Gravity pulls material together. As pressure increases, nuclear fusion begins. Hydrogen atoms combine to form helium. This process releases energy as light and heat. Stars shine for millions or billions of years. Eventually, they change as their fuel runs out. Many stars have planets. These planets form from disks of gas and dust around young stars. Small particles collide and stick together. Over time, larger bodies form. Planets settle into stable orbits. Gravity keeps them moving in regular paths. An exoplanet is a planet that orbits a star outside our solar system. Thousands of exoplanets have been discovered. They vary widely in size, temperature, and composition. Some are rocky like Earth. Some are gas giants like Jupiter. Some orbit very close to their stars. Others orbit much farther away. One common method is the transit method. When a planet passes in front of a star, the star's brightness decreases slightly. Sensitive telescopes can measure this change. Another method is the radial velocity method. A star moves slightly as a planet orbits it. This motion can be detected through changes in the star's light. Light travels at a constant speed. It takes about 8 minutes for sunlight to reach Earth. Light from distant stars can take years or even millions of years to arrive. When we observe distant objects, we see them as they were in the past. Astronomy is a way of looking back in time. Distances in space are extremely large. Astronomers use light years to measure them. 1 light year is the distance light travels in 1 year. The Milky Way is about 100,000 light years across. Most of space is empty. This emptiness creates a sense of calm stillness. In space, sound does not travel. There is no air to carry vibrations. All motion happens in silence. Planets orbit, stars rotate, galaxies drift. Everything moves quietly. Gravity shapes the universe. It holds galaxies together. It keeps planets in orbit. It allows stars to form. Without gravity, structure would not exist. Its influence is steady and constant. Stars live for billions of years. Galaxies change slowly. Planetary systems remain stable for long periods. The universe evolves gently over immense time scales. There is no rush, only gradual change. Astronomers collect data carefully. They analyze light, they measure motion, they test ideas. Scientific knowledge grows slowly and steadily. Discoveries take time. Earth is one planet among many. Our Sun is one star among billions. The Milky Way is one galaxy among countless others. This perspective can feel peaceful. The universe is vast, but ordered. An exoplanet is a planet that orbits a star outside our solar system. The word exoplanet comes from the term extrasolar, meaning beyond the sun. For most of human history, only the planets in our own solar system were known. These included Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. The idea that other stars might also have planets was considered possible, but unproven. This changed in the late 20th century. Advances in telescope technology allowed astronomers to detect planets orbiting distant stars. Thousands of exoplanets have now been identified. Each discovery adds to our understanding of how planetary systems form and evolve. Exoplanets are located in other star systems within our galaxy, the Milky Way. The Milky Way contains hundreds of billions of stars. Many of these stars are likely to host planets. Some exoplanets are relatively close to Earth, only a few light-years away. Others are thousands of light-years distant. Distances are measured in light-years. 1 light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. When astronomers observe distant exoplanets, they are seeing light that left those systems long ago. The first confirmed exoplanets were discovered in the 1990s. Some of the earliest detections were made around pulsars, which are rapidly rotating neutron stars. Soon after, planets were found orbiting sun-like stars. Many of these early discoveries were unexpected. Some planets were larger than Jupiter. Others orbited extremely close to their stars. These findings challenged earlier theories of planetary formation. Scientists realized that planetary systems could be far more diverse than our own. Exoplanets follow regular paths around their stars. These paths are called orbits. Orbits are shaped by gravity. The closer a planet is to its star, the faster it completes an orbit. Some exoplanets orbit in just a few days. Others take many years to complete a single revolution. Orbital distance affects temperature, radiation exposure, and atmospheric conditions. Stable orbits are essential for long-term planetary systems. Exoplanets come in many forms. Some are rocky, similar to Earth, Venus, or Mars. Some are gas giants, like Jupiter and Saturn. Others are ice giants, similar to Uranus and Neptune. There are also super-Earths, which are larger than Earth, but smaller than Neptune. Mini-Neptunes have thick atmospheres, but smaller sizes. Each type forms under different conditions in a protoplanetary disk. Hot Jupiters are gas giants that orbit very close to their stars. Their temperatures can reach thousands of degrees. They often complete an orbit in just a few days. These planets were surprising to astronomers. Earlier models suggested gas giants could only form far from their stars. Hot Jupiters likely formed farther out and migrated inward over time. Their study helps scientists understand planetary migration. Rocky exoplanets are composed mainly of metal and silicate rock. They are similar in structure to Earth. Some may have solid surfaces. Others may have lava oceans or thick atmospheres. Surface conditions depend on temperature, gravity, and atmospheric composition. Some rocky exoplanets are extremely hot. Others may be cold and icy. Gas giants are made mostly of hydrogen and helium. They have deep atmospheres and no solid surface. Ice giants contain heavier elements like water, methane, and ammonia. Their thick cloud layers affect temperature and chemistry. These large planets often influence the orbits of smaller planets in their systems. Planets form from disks of gas and dust around young stars. These disks are called protoplanetary disks. Small particles collide and stick together. Over time, they form larger bodies called planetesimals. Gravity pulls these bodies together to form planets. This process takes millions of years. Different conditions lead to different planet types. Most exoplanets cannot be seen directly. They are detected by observing their effects on stars. The most common method is the transit method. When a planet passes in front of a star, the star's brightness decreases slightly. Sensitive telescopes can measure this change. Repeated transits confirm the presence of a planet. Radial velocity method. Another detection method measures how a star moves. A planet's gravity causes the star to wobble slightly. This wobble changes the star's light spectrum. Astronomers measure these changes to estimate a planet's mass. This method works best for large planets close to their stars. Measuring planet size. The depth of a transit shows how much light a planet blocks. Larger planets block more light. Smaller planets block less. This allows scientists to calculate a planet's radius. Combining this with mass estimates reveals density. Density helps determine composition. This allows scientists to calculate a planet's radius. Combining this with mass estimates reveals density. Density helps determine composition. Estimating planet mass. Star wobble measurements reveal a planet's gravitational influence. More massive planets cause stronger effects. Mass estimates combined with size data provide insight into internal structure. Rocky planets are denser than gas giants. Some exoplanets have thick atmospheres. Starlight passing through these atmospheres changes slightly. This reveals chemical signatures. Gases such as water vapor, carbon dioxide, methane, and hydrogen can be detected. Atmospheric studies help scientists understand climate and weather patterns. Planet temperature depends on distance from its star. Closer planets receive more radiation. Farther planets are cooler. Star type also matters. Red dwarfs emit less energy than sun-like stars. Blue stars emit much more. Habitable zones. The habitable zone is the region where liquid water may exist on a planet's surface. Liquid water is essential for life as we know it. Some exoplanets orbit within this zone. However, atmosphere, gravity, and radiation also affect habitability. Why exoplanets matter? Exoplanets help scientists understand how common planets are in the universe. They reveal how planetary systems form and evolve. They help answer questions about the possibility of life elsewhere. Each discovery adds valuable data. Exoplanets exist in a wide range of environments. Some are exposed to intense heat, others remain locked in deep cold. These conditions depend on distance from a star, the type of star, and the planet's atmosphere. Studying extreme worlds helps scientists understand the limits of planetary formation and survival. The primary factor shaping a planet's temperature is its distance from its star. Planets closer to their stars receive more radiation. Planets farther away receive less. This balance determines whether a planet becomes extremely hot, extremely cold, or moderate in temperature. Orbital shape can also affect heating. Some planets follow elongated orbits, causing large temperature changes over time. Some exoplanets orbit extremely close to their stars. These planets are exposed to intense stellar radiation. Surface temperatures can reach thousands of degrees. In some cases, rock itself may melt. These planets are often referred to as lava worlds. Lava worlds are rocky planets with surfaces hot enough to melt stone. Molten rock may flow across their surfaces. Atmospheres, if present, are often thin or unstable. Extreme heat can cause surface materials to vaporize. These planets provide insight into how rocky worlds behave under extreme conditions. Many hot exoplanets are tidally locked. One side always faces the star. The other side remains in darkness. The day side can be extremely hot. The night side can be much cooler. Atmospheric circulation may move heat between the two sides. Hot Jupiters are large gas giants that orbit very close to their stars. Their atmospheres are heated to extreme temperatures. Strong winds move gases around the planet. Some hot Jupiters show atmospheric evaporation. Gas can be stripped away by stellar radiation. These planets help scientists study atmospheric physics under intense heat. Extreme heat can cause a planet's atmosphere to escape into space. Light gases like hydrogen are lost first. Over time, this can change a planet's composition. Atmospheric loss is especially common around active stars. This process shapes long-term planetary evolution. At the opposite extreme are cold exoplanets. These worlds orbit far from their stars. Some receive very little heat. Surface temperatures may remain far below freezing. Ice can dominate their surfaces and interiors. Many cold exoplanets are gas or ice giants. Their upper atmospheres contain frozen compounds. Methane, ammonia, and water can form icy clouds. Deep inside, pressures and temperatures may still be high. Despite cold surfaces, internal heat can remain. Some rocky exoplanets exist in frozen conditions. Their surfaces may be covered in ice. Oceans, if present, may be frozen solid. In some cases, subsurface oceans could exist beneath thick ice layers. These environments are studied for their potential to support chemistry. Not all planets orbit stars. Some are free-floating, known as rogue planets. They drift through space without a central star. These planets are extremely cold. Heat comes only from internal sources. Rogue planets are difficult to detect, but may be common. Atmospheres play a major role in temperature control. Thick atmospheres can trap heat. Thin atmospheres allow heat to escape. Greenhouse gases increase surface temperatures. Without an atmosphere, planets experience extreme temperature swings. Hot worlds and cold worlds represent opposite extremes. Both types help define the range of planetary environments. Studying them improves models of climate and atmospheric behavior. They also help scientists understand how Earth fits into this range. Extreme exoplanets test scientific theories. They show how planets respond to radiation, gravity, and chemistry. They reveal processes that shape planetary systems. Understanding extremes helps identify planets with more Earth-like. Planets are generally defined as rocky worlds with sizes and masses comparable to Earth. They are composed primarily of rock and metal. They may have solid surfaces. Their similarity to Earth makes them important targets for study. However, no two planets are exactly the same. Earth-like refers to broad physical characteristics, not identical conditions. Planet size and mass strongly influence surface conditions. Planets similar in size to Earth are more likely to retain an atmosphere without becoming gas giants. If a planet is too small, it may lose its atmosphere. If it is too large, it may collect thick layers of gas. Earth-sized planets occupy a narrow range where rocky surfaces are possible. Earth-like planets are made mostly of silicate rock and metal. Iron-rich cores generate gravity and internal heat. Mantles and crusts shape surface geology. This structure allows for mountains, plains, and volcanic activity. Geology plays a role in climate regulation over long periods. Stable orbits are essential for long-term planetary conditions. Earth-like planets typically follow nearly circular orbits. This reduces extreme temperature variation. Highly elongated orbits can cause large swings in climate. Long-term stability supports consistent surface environments. The habitable zone is the region around a star where liquid water may exist on a planet's surface. Liquid water requires moderate temperatures. If a planet is too close to its star, water may evaporate. If it is too far, water may freeze. Earth orbits within the Sun's habitable zone. The type of star affects planetary conditions. Sun-like stars provide stable energy over billions of years. Red dwarf stars are smaller and cooler. Their habitable zones are closer to the star. Planets in these zones may become tidally locked. Stellar activity can also influence atmospheres. An atmosphere regulates surface temperature. It traps heat through the greenhouse effect. It protects the surface from harmful radiation. Atmospheric composition matters. Gases such as nitrogen, carbon dioxide, and water vapor influence climate. Earth's atmosphere evolved over time. On Earth, geological processes help regulate climate. Volcanic activity releases gases. Weathering removes carbon dioxide. These processes balance temperature over long timescales. Earth-like planets may have similar cycles. Water plays a central role in planetary habitability. It shapes landscapes. It moderates temperature. It enables complex chemistry. On exoplanets, water may exist as oceans, ice, or vapor. Detecting water is a major goal of exoplanet research. Magnetic fields protect planetary atmospheres. They deflect charged particles from stellar winds. Earth's magnetic field shields the surface. Planets without magnetic fields may lose atmosphere more easily. Magnetic activity depends on internal structure and rotation. Earth-sized planets are difficult to detect. They cause only small changes in starlight. Sensitive instruments are required. Transit depth is shallow. Radial velocity signals are weak. Despite this, many Earth-sized exoplanets have been found. Atmospheric studies focus on how light passes through a planet's atmosphere. Specific gases absorb specific wavelengths. By analyzing this light, scientists identify chemical components. This method is called transmission spectroscopy. It provides clues about climate and composition. Even planets similar in size and orbit can differ greatly. Some may be hotter, some colder. Some may lack water. Others may have thick clouds or dense atmospheres. Earth-like is a starting point, not a guarantee of habitability. Earth-like planets help scientists understand how common rocky worlds are. They provide insight into planetary evolution. They help place Earth in a broader cosmic context. They guide future exploration. Certain exoplanets are studied more closely than others. They may be nearby, they may orbit small stars, they may be similar in size to Earth, or they may display unusual properties. These characteristics make them easier to observe and scientifically valuable. Proxima Centauri b orbits Proxima Centauri, the star closest to the Sun. The star is a red dwarf located just over 4 light-years away. Proxima b has a mass similar to Earth. It orbits within its star's habitable zone. Because of its proximity, Proxima b is one of the most studied exoplanets. The planet likely experiences strong stellar activity. Flares from the star may affect its atmosphere. TRAPPIST-1 is a small red dwarf star. It hosts 7 known planets. All 7 are similar in size to Earth. Several orbit within or near the habitable zone. The planets are tightly packed. Their orbits cause frequent gravitational interactions. This system allows scientists to compare multiple rocky worlds around the same star. Kepler 186f was one of the first Earth-sized planets found in a habitable zone. It orbits a red dwarf star. The planet is slightly larger than Earth. Its distance from the star suggests moderate temperatures. However, its atmosphere remains uncertain. Kepler 186f demonstrated that Earth-sized planets in habitable zones exist. Kepler 452b orbits a star similar to the Sun. The star is older and slightly brighter. The planet is larger than Earth. It orbits within the habitable zone. Because of its size, it may be a super-Earth, rather than a true Earth-like planet. Its discovery expanded the search to Sun-like stars. 51 Pegasi b was the first exoplanet discovered around a Sun-like star. It is a gas giant. It orbits extremely close to its star. Its orbital period is only a few days. This discovery challenged earlier models of planetary formation. It showed that giant planets can exist close to stars. WASP-12b is an extremely hot gas giant. It orbits very close to its star. Temperatures exceed 2,000 degrees. Its atmosphere is being stripped away by stellar radiation. The planet has an extended, comet-like tail of gas. WASP-12b helps scientists study atmospheric loss. HD 209458b was one of the first exoplanets observed transiting its star. It provided clear measurements of planetary size. Scientists detected atmospheric gases escaping from the planet. This observation confirmed that atmospheres can be studied directly. Some famous exoplanets fall between Earth and Neptune in size. These planets are common in the galaxy. They often have thick atmospheres. They may be rich in hydrogen, helium, or water vapor. The diversity challenges simple planet classification. Nearby exoplanets are easier to observe. Their light signals are stronger. Atmospheric studies are more feasible. Future telescopes will focus on nearby systems. These worlds are key targets for continued research. Famous exoplanets show the diversity of planetary systems. They demonstrate that Earth's configuration is not universal. They refine theories of planet formation and evolution. Each discovery improves scientific models. Many famous exoplanets are observed repeatedly. Long-term data reveals changes over time. Atmospheric behavior can be monitored. Orbital stability can be confirmed. Scientific understanding increases gradually. Every planetary system begins with a star. Stars form from large clouds of gas and dust. As gravity pulls material together, a central star ignites. The remaining material forms a rotating disk around the star. This disk becomes the source of planets. The properties of the star shape everything that follows. The mass of a star determines the strength of its gravity. More massive stars pull more material inward. This affects how much matter is available to form planets. Large stars tend to have shorter lifespans. Smaller stars burn fuel more slowly and last much longer. Planetary systems must form and evolve within these time limits. Stars come in different types based on size and temperature. Red dwarf stars are small and cool. Sun-like stars are medium-sized and stable. Blue stars are large, hot, and short-lived. Each type influences planetary environments differently. Around young stars, disks of gas and dust are common. These are called protoplanetary disks. The disk's temperature varies with distance from the star. Closer regions are hotter. Farther regions are cooler. This temperature gradient determines what materials can solidify. Near the star, only metals and rock can survive. This leads to the formation of rocky planets. Farther out, ice and gas can accumulate. This allows gas giants and ice giants to form. The star's energy output controls this separation. Stars emit radiation across many wavelengths. Visible light provides warmth. Ultraviolet radiation can affect atmospheres. X-rays can strip atmospheric gases. Planets close to active stars receive intense radiation. This can change surface and atmospheric conditions. Stars release streams of charged particles. These are known as stellar winds. Strong stellar winds can erode planetary atmospheres. Planets without magnetic fields are especially vulnerable. Stellar wind strength varies with star age and activity. The habitable zone depends on star luminosity. Brighter stars have habitable zones farther out. Dimmer stars have habitable zones closer in. Planets must remain within this zone for long periods. Orbital stability is essential for long-term habitability. Planets close to their stars may become tidally locked. One side always faces the star. The other side remains dark. This affects temperature distribution. Atmospheres may help transport heat. Star type influences how extreme these effects are. Some stars are highly active. They produce frequent flares. Flares release bursts of radiation. These events can heat atmospheres or remove gases. Red dwarf stars are especially active early in their lives. Planet survival depends on timing and protection. Stars interact with planetary magnetic fields. Strong magnetic fields protect atmospheres. They deflect charged particles. Planets with weak or no magnetic fields may lose air over time. Star-planet interactions shape long-term evolution. Star lifetimes vary greatly. Large stars may last millions of years. Sun-like stars last billions. Red dwarfs can last trillions of years. Long-lived stars provide extended stability for planets. Time is an important factor in planetary development. Stars influence planetary movement. Interactions within the disk can cause planets to migrate. Some planets move inward, others move outward. Migration shapes final planetary positions. Hot Jupiters are likely the result of migration. Some planets orbit stars in binary systems. Two stars influence gravity. Orbits can be complex. Planetary stability depends on distance and alignment. Despite complexity, stable planets can exist. Stars determine planetary composition. They control temperature and radiation. They influence atmospheric survival. They set the pace of planetary evolution. Understanding stars is essential to understanding planets. Astronomers study stars and planets together. Stellar observations improve planet models. Future telescopes will examine star-planet interactions in detail. knowledge grows gradually and steadily. For centuries, humans have wondered whether life exists elsewhere in the universe. In modern science, this question is approached carefully. Researchers rely on evidence, observation, and testable hypotheses. Rather than asking whether intelligent life exists, scientists first ask a simpler question: can life, in any form, exist beyond Earth? In science, life is defined by certain characteristics. Living systems use energy. They maintain internal order. They grow and change. They can reproduce. They respond to their environment. On Earth, all known life is based on chemistry, involving carbon and water. This provides a starting point for searching elsewhere. Water is essential for life as we know it. It dissolves chemicals. It enables complex reactions. It remains liquid over a wide range of temperatures. For these reasons, scientists focus on planets and moons where liquid water may exist. This includes surface water and subsurface oceans. The habitable zone is the region around a star where temperatures may allow liquid water. Planets in this zone receive moderate energy. However, being in the habitable zone does not guarantee habitability. Atmosphere, pressure, and radiation also play important roles. Atmospheres protect surfaces from radiation. They regulate temperature. They transport heat and chemicals. Certain atmospheric gases are associated with biological activity on Earth. These include oxygen, methane, and carbon dioxide. Detecting these gases elsewhere is a major research goal. A biosignature is a chemical or physical sign that may indicate life. On Earth, oxygen is a strong biosignature. However, oxygen can also be produced without life. Scientists look for combinations of gases that are difficult to explain by non-biological processes. Multiple lines of evidence are required. Life on Earth exists in extreme environments. Some organisms live in boiling water. Others survive deep underground. Some endure intense radiation. These extremophiles expand the range of possible life-supporting conditions. They suggest life may exist in places once considered uninhabitable. Some worlds may have liquid water beneath ice layers. Heat from internal processes can keep water liquid. On Earth, deep ocean environments support life without sunlight. Similar conditions could exist on distant planets or moons. These environments are considered promising targets. Life requires energy. On Earth, sunlight is the primary source. However, chemical energy can also support life. Chemical reactions near hydrothermal vents sustain ecosystems. This expands the range of possible habitats. Life takes time to develop. Planetary systems must remain stable for long periods. Frequent impacts or intense radiation can disrupt development. Long-lived stars provide more opportunities for life to emerge. Time is a critical factor. Star type influences habitability. Stable stars provide consistent energy. Highly active stars may strip atmospheres. Red dwarf stars pose challenges, but also offer long lifetimes. Each star type presents different conditions. Detecting life on exoplanets is extremely difficult. Planets are faint, signals are weak. Atmospheric measurements require precise instruments. Future telescopes aim to improve sensitivity. Progress is gradual. Some research looks for signs of technology. Radio signals are one example. This search is cautious and systematic. No confirmed signals have been detected so far. Scientific standards remain high. The universe contains billions of galaxies. Each galaxy contains billions of stars. Many stars host planets. Even if life is rare, the scale of the universe makes it possible. Probability alone does not provide certainty. Evidence is required. Science proceeds carefully. Extraordinary claims require strong evidence. Hypotheses are tested and retested. The search for life is ongoing and methodical. Studying life beyond Earth helps scientists understand life itself. It places Earth in a broader context. It deepens knowledge of biology, chemistry, and planetary science. The question is fundamental, but approached with patience. No confirmed evidence of life beyond Earth has been found. However, many environments appear potentially suitable. Research continues. Observations improve. Understanding grows steadily. The universe is approximately 13.8 billion years old. This age is measured through observations of cosmic expansion and radiation. Compared to human timescales, cosmic time moves slowly. Stars live for millions to trillions of years. Galaxies evolve gradually. Change occurs over immense spans of time. Observations show that the universe is expanding. Galaxies are moving away from one another. This expansion is driven by a phenomenon known as dark energy. As time passes, distant galaxies will move beyond observable reach. The universe will become increasingly empty on large scales. Stars form from clouds of gas and dust. Over time, this material is used up. As the universe ages, fewer new stars will form. Existing stars will continue to shine. Eventually, star formation will slow and then largely cease. The universe will grow darker. Small stars, such as red dwarfs, burn fuel very slowly. They can shine for trillions of years. These stars will dominate the far future of the universe. Around them, planets may remain stable for extremely long periods. Time will stretch quietly onward. Planetary systems change slowly. Orbits remain stable for long periods. Over immense time, gravitational interactions may alter paths. Some planets may be ejected into space. Others may drift inward. Most changes occur gradually and quietly. Stars do not last forever. Sun-like stars expand into red giants. They shed outer layers. Their cores become white dwarfs. Larger stars may explode as supernovae. Their remnants become neutron stars or black holes. These processes enrich space with heavier elements. Black holes are regions of intense gravity. They grow by absorbing matter. Over vast time periods, even black holes may slowly lose mass. This process is known as Hawking radiation. It occurs extremely slowly. Black holes will persist far into the future. As expansion continues, temperatures will drop. Energy will spread thinly across space. Stars will fade. Galaxies will dim. The universe will approach a state of maximum entropy. This is sometimes called heat death. Atoms will remain. Particles will continue to exist. Interactions will become rare. Most matter will be cold and quiet. Motion will slow. Change will become subtle. In the far future, the universe may contain few shining stars. Light will be scarce. Space will be vast and dark. Yet physical laws will still operate. The universe will continue. From this long view, the present moment is brief. Stars still shine brightly. Galaxies are active. Planetary systems are young. Life exists on at least one world. This period is rare and valuable. Some details of the future remain uncertain. Dark energy is not fully understood. New physics may alter predictions. Science continues to refine models. Understanding grows gradually. The universe has a long future ahead. Its changes will be slow, quiet, steady. Stars will rise and fade. Galaxies will drift apart. Time will continue without urgency. As the universe moves gently forward, there is no need to hurry, no need to follow every detail. The cosmos will continue its slow unfolding. Stars will glow where they remain. Space will stretch quietly outward. You may rest. You may let your thoughts fade. The universe will carry on, calm and untroubled, long after this moment passes.